Hi, welcome back to my channel. My name is Gina. In this video, let's derive the Doppler effect formula. Doppler effect is a phenomenon in physics when the frequency is altered due to the motion of observer relative to the source. We're going to consider two cases. First case is we have a stationary source with a moving observer. For example, a car is at rest, it's honking at an observer that is moving toward the car or away from the car. And second case is the opposite. We are going to consider a stationary observer with a moving source. Let's start with the first one. When we have stationary car with an observer that is moving toward the car at the speed of VO, O for observer. The source emits sound, and we can characterize the sound by its frequency or the wavelength. Wavelength is the wave speed divided by frequency. If the observer is moving toward the source, then the rate of the wave crest reaching to the observer would alter. For example, if at the beginning the observer is also stationary, then the rate that the wave crest reaches the observer would be constant. But if the observer is moving toward the source, then the speed of the wave crest reaching to the observer will increase. And what would that be? That would be the original wave speed plus the speed of the observer, VO. Then what would be the perceived frequency by the observer? Let's call the perceived frequency F prime. Frequency is wave speed divided by wavelength, and we just found that the wave speed would change if the observer is moving. So F prime is V prime divided by wavelength. V prime is original wave speed plus the speed of observer. So F prime is V plus VO divided by wavelength, and wavelength is wave speed divided by frequency. And we can use the same argument for when an observer is moving away from the source. The speed of wave crest relative to observer in that case would be V minus VO. So we'll get two forms. F prime for observer that is approaching the source would be original wave speed plus speed of observer divided by original wave speed and times the original frequency. This is for observer approaching the source. For when an observer is receding, instead of V plus VO, we have V minus speed of observer divided by wave speed and times the original frequency. And this is for observer receding the source. Now let's look at the second case, when the source is moving and observer is stationary. When the source is moving, the wavelength will be altered. You can imagine it as the original wavelength is something like this, or original wave. But if the source, say that is the source, is moving in this direction, then the wavelength will be compressed. So the altered wave will look like this. So how can we write down a form for the observed wavelength? Observed wavelength, let's call it lambda prime. It will be the original wavelength minus some delta x. Delta x will be the distance traveled by the source for one cycle. So lambda prime would be lambda minus speed of the source, es, times the time for one cycle, which is the period. Let's rewrite wavelength as wave speed divided by frequency. And let's also write the period as 1 over frequency. So minus speed of source divided by frequency. Now what would be the frequency perceived by the observer? F prime. It would be original wave speed divided by altered wavelength, which is wave speed divided by wave speed divided by frequency minus speed of source divided by frequency, which equals to original wave speed over B minus Bs times F. Similarly, we can use the same argument for when the source is moving away from the observer. So again, we are going to get two forms. First form is for when the source is moving toward the observer. It would be wave speed divided by wave speed minus speed of source times original frequency. This is for source approaching. The second form, F prime, for a source that is receding, then instead of compressing the wavelength, the waves will be stretched. So in the denominator, we have original wave speed plus speed of source and times the original frequency. This is for source receding. Now let's combine the results. We just found that when the observer is moving, then the speed of wave crest will alter, which also changes the frequency. So the perceived frequency will be wave speed plus speed of observer divided by wave speed times frequency for when the observer is approaching the source. And when the observer is receding, in the numerator we have wave speed minus speed of observer. And second case is when the source is moving. When the source is moving, then the wavelength will be compressed or stretched. So the perceived frequency will be wave speed divided by wave speed minus speed of source times frequency for source approaching the observer. And for source that is receding the observer, in the denominator we have wave speed times speed of source. Now can we write down one single equation to combine these four equations? The perceived frequency would be original wave speed plus or minus speed of observer plus for when an observer is approaching and minus for when an observer is receding. Then divided by original wave speed minus or plus speed of source minus for when the source is approaching and plus for when the source is receding and times the frequency. And that is the Doppler effect formula. And that is the end of the video. If you have any questions, feel free to comment below. If you like my videos, please like and subscribe. Next week, we are going to look at an example of Doppler effect.